Thank you, Tobias, for the nice introduction. And I also want to thank Dan and Ricardo for the invitation. So there are actually hundreds of sensors in a car. However, let's have a show of hands. How many of you are wearing at least one sensor on your body right now? So not everyone, right? Not even one sensor per body. So essentially, our human body is just a soft living machine that's continuously radiating multimodal, distributed, and personal data about our health, our status, our intentions, and emotions. For example, across any 2 points on the surface of our skin, there is a very subtle electrical potential. On the chest, the signal is from the heart, that is called electrocardiogram. On the scalp, signal is from the brain, and that is called the electroencephalogram or EEG. And across our eyes, because our eyeballs are dipoles, their rotation actually induce surface potentials called electrooculogram. We can actually use that to detect eye movement and saccades. And those are electrical signals. There are also mechanical signals, right? Our heartbeat, you can feel by your fingertip. That is called seismocardiogram or SCG. There is blood flowing, pressure, rate, and other kinds of body motion. And there are thermal signals. We can also use optical interrogation. So it's really multimodal from head to toe, right? If we can have a continuous, reliable, high fidelity methodology to acquire all of those data and keep updating this digital twin of our body in the cyberspace, it can unleash this unlimited applications, really, including personalized medicine, human-robot interaction, as well as mixed reality and metaverse. We have someone from Meta today. So the question is, what our current wearables look like? Well, we call them chips on tapes or bricks on straps. That's because they are based on intrinsically rigid and brittle silicons, and therefore they have only limited sites that can be worn, like strapped on the wrist or clipped on our fingertip. Imagine that if we can convert those conventional wearables into the form factor of a temporary tattoo sticker that we can stick to any part of our body with multimodal continuous sensing, then we are closer to the goal of building a digital twin of the body. And the question is, how can we convert those intrinsically stiff and rigid metals and silicons into this skin soft tattoos? Well, we can draw inspirations from 3D compression springs made out of intrinsically very stiff copper or stainless steel. And similarly, if you can cut a piece of aluminum foil into this 2D spring, which we call serpentine ribbons, they become a stretchable conductor. And following this idea, my coworkers and I can shrink this aluminum foil cut by 100 times in the lab, and we can create the first electronic tattoo back in 2011. And this is really a sticker-like wearable that includes all kinds of high-performance inorganic metal, silicon, transistors, and diodes, but it really behaves just like a secondary skin without being obstructive to any of our motion, and it's mechanically imperceptible to wear. After 12 years of development, e-tattoos have grown into a gigantic field. There are a lot of new innovations related to the property of the tattoo, the materials you can use, the functionalities and applications, and also the areas, locations that you can wear. So today, I'm just going to give you two quick examples. One is for heart monitoring, one is for brain monitoring. So the heart is the engine of our body that pumps blood, oxygen and nutrition throughout the body. Whenever we have heart discomfort and visit a cardiologist, the first thing you would get is greeted by a very nice nurse who would put a bunch of electrodes and cables on your chest, like the picture showed by Lee. And after an hour, when you're very busy, cardiologist finally comes to the room. Instead of listening to you, they would listen to your heart. Literally. And this is because in addition to electrocardiogram, they also want to obtain the mechanical activities of the valve opening and closing. However, a stethoscope requires pressure against the chest to function, and it is not easy to make as a wearable. So our group has engineered the first wearable electromechanical cardiac sensor by using gold electrodes for ECG and piezoelectric serpentine membranes as the SCG sensor. And the synchronous and simultaneous measurement of ECG and SCG not only tells you all the characteristic QRS peaks or the aortic valve opening, mitral valve closing peaks, but also telling you all kinds of cardiac time intervals, such as the pre-ejection period, left ventricular ejection time, systole, diastole, and so on. So SCG is essentially similar to the phonocardiogram measured by the stethoscope, just a little bit lower frequency. And this year, finally, we got rid of all the cables and wires and have a completely mobile wireless ambulatory ECG, SCG, ETA2. The softness and conformability to the chest, as well as the lightweight, really minimize the mechanical impedance between our tissue and the electronic devices, which can therefore give us very high fidelity electromechanical sensing. And here is a video showing that we can measure 3 axes of SCG. Those are the black channels, as well as a 1-channel ECG, which is the red channel. And when he starts to walk, you can see that actually the ECG still remains very high quality, but there is a lot of motion signal because the SCG sensor is a motion sensor. It is doing what it's supposed to do. We can use advanced data analytics to still extract those SCG signal embedded in those motion. And this is using an echocardiogram to confirm that the peaks in SCG are indeed reflecting the aortic valve opening and closing. And we can validate our wireless ECG, SCG, ETA2 using an FDA-cleared non-invasive cardiac output monitor, which gives us LVET, like a ground truth reading. And we can exercise the subject. And this is a desktop device. You can see those cables and electrodes for ICG. And our LVET correlation with the NICOM is 0.955. And the mean error in this plot is only 0.44 millisecond. But this is only when we can extract during the rest. So during the exercise period, we still need to develop better algorithm to do that. And if we compare our wireless chest ETA2 with other chest sensors available in the literature, we can see that we achieve simultaneous low weight and low power draw, which is very important for wearability and long-term sensing. And because there are no long-term mobile SCG sensors, we can compare just the heart rate measured by a smartwatch versus the ETA2. And we can see this heart rate works very reliably even under a lot of like daily activities. But what smartwatches cannot do is to measure the cardiac output from the heart, which has to be measured as a gold standard, measured by invasive catheters. Cardiac output represent the volume of the blood that can be pumped by our heart every minute. And that's the most direct indicator of the strength and health of one's heart. And you can see that the NICOM and the eta2 measured cardiac output also get very good correlation. This is still a work in progress. Well, so enough about heart. How about our brain? We know that I need to be careful when I speak about MRI, but I think it's consensus that MRI offers nice spatial resolution, but EEG offers nice temporal resolution down to milliseconds. And this is basically reflecting the electrical activities of the pyramidal neuron postsynaptic potentials, but you can directly measure non-invasively from the scalp. And clinically, there are very bulky, time-consuming, and uncomfortable EEG sensors. Non-clinically, there are also dry finger or comb-shaped EEG sensors. And eta2s can also be applied on bald heads to measure EEG. However, most of us have hairs. So how to acquire EEG using eta2s, but still with hairs. Before talking about eta2, I just want to highlight our most recent publication that we have engineered sponge electrodes that can be simply laminated onto a VR headset without damage the VR headset, and we can measure, in this case, 9 channels of EEG during the VR immersive experience. And in this case, we are just showing an example of EEG, which is called a contingent negative variation that occurs between a stimulus and the quick motor response to this stimulus. So this is when the user is having a driving game in the VR, and we can see the negative potential clearly. So this is a hair compatible, not too dense of hairs, but if we can have soft sponges that can still access some of the scalp skin, it could work. And what wild idea we would like to propose is actually leveraging additive manufacturing. So what we want to propose is that now, because we have so many 3D printing technologies available, can we directly print eta2s on human body? And that requires a 3D digitization, a scan of the head. And then we can have a digital shape of the head where we can do customized, personalized design of the electrodes that can be placed at the exact clinically desirable locations. And then we can pass this design into the G code of a tool path to control the print head that can print directly on head. Even though there are hairs, currently only works for buzz cut, the inkjet can still jet through the hairs and wet the roots of the hairs and conform to the microscopically rough skin surface. This is a slow motion of the non-contact inkjet printing of a conductive ink that can jet through those micro hairs on the arm. And as jetted, it's a liquid. It can conform to whatever surface roughness we have. But after 15 minutes, this ink can self-dry and cure under room temperature on the skin, and it become a thin conductive film, complete dry, of a thickness around 20 micron. And this is to show the scanning process. Now, because of the Face ID is leveraging the True Depth iPhone camera, we can just use an iPhone to scan and digitize our head. And after digitizing and designing, now we can do printing. And of course, we have fiducial points like this laser point to ensure all safety protocols. And here we are inkjetting electrodes. Electrodes need to have ultra low contact impedance with the skin. So this electrode has some salt in it. And after we inkjet all the designed electrodes at the desirable positions, next we can jet the interconnects, connecting each of the electrode to the back of the neck, where we can connect amplifiers. And here is a comparison of the EEG recorded by the printed electrodes versus those conventional shower cap gel-based electrodes. And we have a lot of data, but here I'm just showing very simple alpha rhythm. When our eyes are closed, this 10 Hertz alpha rhythm shows up. Eyes open, they disappear. Very comparable spectrum. The uniqueness of this printed electrodes are that not only they are dry and hair compatible, but also as printed, they have slightly lower contact impedance even compared with the gel electrodes because they have this perfect conformability with the skin. But after 6 hours, we can see that the gel electrode impedance skyrocketed because they dry under room temperature. But those printed thin films, they are already dry thin films. Their impedance only changed very marginally. Currently, those printed thin films are not fully compatible with sleeping because if you scrub on them, they still flake off. But we hope to improve the adhesion of the ink. And another future direction is that because there's no metal involved, this is just a conductive polymer and ultra thin and no closed loop patterns. We hope that we believe it could be MRI compatible. So if that is the capability, then we can have simultaneous imaging, spatial and temporal imaging of the brain. With that, I would like to conclude by saying that ETA2 is a platform technology that can help digitize the human body. Today, I only have time to talk about our heart and brain sensors, but our lab is developing a lot of different types of sensors, especially I was mentioning to Dan that we're also very passionate about wearable imaging in addition to wearable sensing. So we are developing wearable ultrasound. And there are many other like biochemical modalities which my lab is not working on, but there are many, many experts in this field. And what's important is once you put those multimodal, multi-location data together, we will hear about data in a minute, then the fusion becomes really powerful in terms of understanding, predicting, diagnosing, and tracking. So looking forward, I think there are wide open opportunities in wearables in terms of materials, electronics, data, and even close the loop of sensing, edge computing, diagnosis, and therapeutics. However, that is accompanied by a lot of challenges, and all of them are quite important. Currently, we still lack a lot of ground truth outside of clinical lab settings. The quality of data in uncontrolled environment is still a big concern. Identifying, extracting digital biomarkers for health conditions is a big field of research. How do we preserve safety, security, privacy, and so on? Ultimately, without the buy-in of stakeholders like patients, doctors, data centers, insurance, regulatory agencies, those ETA2 technologies will not have a life. With that, let me thank my wonderful group at UT Austin. This is on the Lake Travis, so we have beautiful lake in Austin. And we are a group composed of electrical engineers, mechanical engineers, biomedical engineers, material scientists. And also I want to thank all my sponsors for their generous support. And of course, thank you so much for your attention.
Yeah, thank you, Dr. Liu, for this super exciting talk. Are there any questions? Or maybe I'll start with a question. So the obvious question is, do you have any experience using these sensors in MRI scanners? Because in MRI, like for cardiac imaging, we often use ECG electrodes. And in the typical clinical workflow, it takes often very long to put these electrodes on. And that can lead to the scanner not acquiring data, and that's not good in terms of efficiency. So if it would be possible doing that prior to bringing the patient into the room using such wireless tattoos, that would be super, super good.
Yes, that's true. So the nice thing about ETA2s is both this easy usability and comfort and the long-term tracking. So we have not put our ETA2s under MRI, but one of the ETA2s on the boat head was validated under MRI. And that was still based on gold nanomembrane. So they have to design the serpentine patterns to not have any closed loop features, and that could work if it's nanometer gold. Our conductive polymer would be even better.
Lee?
So regarding your question, I think even if we cannot use it inside the MR scanner, we can do one before and one after the scanner, and because the patient will wear the device continuously, so we can keep monitoring. And then I do have a question that you mentioned the exercise. Can you get a reliable signal, ECG signal, or heart signal, or the breathing signal at stress? That will be, I think, very important, especially when you do the monitoring while the stress is increasing.
Yeah, that's also something we are considering right now. So ECG could be very reliable even under excessive motion, because the ETA2 really ensures no relative motion between the skin and the electrode, even under a lot of skin deformation, right? So those relative motion are giving us a lot of tribal electric artifacts, which we eliminate, but we cannot eliminate the skin impedance change due to motion, but that's actually a smaller component. So that's why our heart rate is so well correlated with the smartwatch measurements during arbitrary daily activities. What's hard is SCG, because SCG itself is measuring this 5-micron vibration of the chest skin due to heartbeat after filtering all the breathing signals. And if we could get accurate SCG during stress, that means we can give you all the time intervals as well as cardiac output during exercise, and that is super valuable. Currently, we can achieve SCG sensing under mild motion, like a slow walking or jogging. That works, but high speed, the noise is too much. We need to talk to data scientists to help us.
Just following up on that, by analogy with the ECG, where there's other sorts of potentials, by using differential potentials, we can then derive these famous EKG leads. Similarly, if we have sort of an array of accelerometers around your tattoo for looking for the regional motions centered over the heart, then perhaps you can triangulate between the adjacent reference areas and try to block or null the effective bulk motion to see what's the differential motion at the center of that triangle.
That's exactly what NICOM is doing. They are using this impedance cardiography to extract the cardiac output using those electrodes. But even NICOM does not promise performance under motion.
Excellent. Maybe one quick last question. How long does these sensors last? How long can you wear them?
Right, that's a great question. The sensors never break. Actually, we designed them to be mechanically robust to any kind of body motion. I never got caught through the airport security either. But our skin exfoliates and builds up dead cells on the interface. So after about like 10 days, we start to see signal degradation. But the motion is still very good.
Excellent. Thank you very much.
Thanks.
Okay, I think let's thank Dr. Liu again for this wonderful talk.